Alright guys, welcome back to yet again another video. Today we're going to be covering linear optimization. Okay, so linear optimization is a bit of a weird idea, and we're going to have to think about we're going to use what we have learned in our previous lessons to find out what linear optimization is. So we're going to be working again with 3D objects like we did before. So I want to imagine, let's say that we have an XY plane. So here we call this is our X axis, and right up here is our Y axis, like that. But now we're using 3D objects, and so we have a third variable, which adds a third dimension. So let's just say coming up above this plane, we have our z-axis right there. So it's a 3D object. So that is our z-axis, our third variable. Now, on the xy plane, let's just imagine it as if it's a sheet of paper. And then on top of that sheet of paper, you have a half circle, a semi-sphere, a half sphere, cake, because everyone likes to make cake into weird objects these days, right? So let's just say we have a cake on top that's a half of a sphere. Alright, now let's say for a moment that we cut a rectangular square that goes all the way to the bottom, and we pull that piece of cake out, and then we're left with what we have here. Let's call this our piece of cake. Alright, so follow me here. Now, since it's a sphere, and it gradually goes up like that, that means that where these corners are, they're actually at different heights from the XY plane, from the piece of paper, or the plate you might say. So those legs are at different heights. So what we can do with linear optimization will allow us to find the height of each of these legs right here. All four of those legs. So that's a pretty cool idea if you think about it. Again, we're trying to find the height, and we want to find the lowest and the highest point in that piece of cake. So let me go ahead and just dive right into an example of how we can find that. So we're going to be using all of what we've used in the previous lessons, from solving systems of equations in 3 variables and 2 variables, and then we're going to be graphing inequalities. So first of all, on this xy plane, let's go ahead and graph the system of linear inequalities that we have here. But before I continue, there's one thing I wanted to add. If we can, just for a moment, imagine if we're looking down from, if there's a top-down view of this plane right here. So let's just say this xy plane, this is the sphere, as if we were looking down above it. Okay, and then so that's a 3D sphere, but we're just looking at the y and the x plane right now, so we're not thinking about the z dimension. And then this area right here is a region. This region on our xy plane just looks like a regular square, something like that. Just looks like that. And so I want you to envision that as we continue, because that's how we're going to find the length of the legs. So let's go ahead and start. So these are these equations, we're gonna call them constraints. But let's go ahead and graph what these constraints are, and I'll kind of clarify on what the constraints do. All right, so I have color coded my lines. So x plus y is less than 20. Well, we could also say we can subtract the y from both sides and say y is equal to negative x plus 20, right? So let's go ahead. That's supposed to say 20. Okay, so we know that it crosses the y-axis at 20, and it has a slope of -1. So that's just going to go right down there. And then, continuing on from when we were graphing inequalities, we have to remember that this is less than and not equal to. So what that means is that we are going to make this a dashed line. Alright, now let's move on to our next equation, where we had 3x plus 4y is less than 72. Let's go ahead and solve for y. So minus 3x minus 3x. So we have 4y is less than negative 3x plus 72, and divide by 4. So then we have that y is less than, we have negative 3 over 4x plus, and then 72 divided by 4, that should be, I think it's 18. Let me go ahead and double check on my calculator. 72 divided by 4 is 18. Alright, so we have our next equation. So it crosses the y-axis at 18. And then we have a slope of negative 3 over 4. 1, 2, 3 over 1, 2, 3, 4. Just like that. Now, if we want to find the x-axis, let's put a 0 in for our y. So if we have 0 is less than negative 3 over 4x plus 18. And then let's go ahead and add our 3 over 4x over here. It's less than 18. Times by 4 divided by 3 times by 4 divided by 3. We have our x alone, so that means x, well, we're not solving an inequality, so this is x is equal to, well, if we do 18 times 4 divided by 3, we're going to be left with 24. So we know on the x-axis, when y is 0, right there. And then let's make sure that we know what our inequality is. It's less than, so we're going to have a dashed line. Alright. Now time for the shading. Let's go back to our blue line. Now it says less than, so we're going to shade beneath our line. So that's going to be right here. Beneath the blue line, we shade. Alright, now let's go to our orange line. And it is also less than, so we shade below this line right here. And now we have to examine the crossover, the double shaded areas, which goes from here to that point down to here. Alright, so we have our region. Just like we did in the last lesson, we have a region. Now I hope you guys don't mind, but I'm going to erase all this because I'm going to need the space. Alright, so now what we need to do, just like in the last lesson in graphing inequalities, is we want to find the vertices of this enclosed region. So right there, there's a vertice, and there's a vertice, and there's one, and we have one down here. Excuse me. So now we want to find out where they are. Also, sorry, just one thing to note, that we also have these inequalities right here. That is supposed to say 0, not w. But what that's saying is that x is greater than 0. So if we're thinking in our x right here, this is where x is 0, right? So x is greater than 0. And then it says y is also greater than 0. So this is our y direction, so y is greater than 0. So we technically have a line here, and we have a line here with our inequalities pointing upwards. So I forgot to mention that, but make quick note of that because that will come up in other problems. Okay, so back to finding the vertices. So one vertice that, well, most of the vertices we already found by graphing them, right? This vertice right here, that was at point 0, 18. And then this one right here was at 20, 0. This one right here is at 0, 0. So really the only one left to find is right here. What is that one? So we know that that is where both our blue and our orange line intersect. So let's go ahead and solve our system of equations. So we have x plus y. We're not using the inequality, so I'm just going to write equals. And then 3x plus 4y equals 72. Now if we solve the system of equations, we can find where they intersect. So I guess what I'll do, again, I'm going to manipulate this equation by multiplying it by negative 3. So then we have negative 3x minus 3y is equal to negative 60. And then we're still left with 3x plus 4y equal to 72. Now let's go ahead and add. So we eliminate our x variable, and then we're just left with y is equal to, well, the difference between 72 and 60 is 12. So we know that our y value is 12, and now we just need to plug that 12 into one of our original equations. I'm going to plug it into the first equation. So x plus 12 is equal to 20 minus 12 minus 12. So x is equal to 8. Yeah. So at 8, 12 is where these two lines intersect. So now I have the vertices of the enclosed region that we have. So let's go ahead. So all of this up to this point should be nothing new. We've already gone through this in the last couple of lessons. This is stuff you already know how to do. Now we're going to get into the linear optimization of this. So what are the vertices of the enclosed region, and write them in this table? Well, we had 0 and 0. We had 0 and 18. There was, 20 and 0. And 8 and 12. Alright, so we used the constraints right here, and then we went ahead and graphed those inequalities. And now this right here, this is what we call as our objective function. This right here is actually a 3D model because there's a third variable. This is so the independent variable in this case is z. The dependent variable is z, but we have two independent variables, x and y. So I'm going to show you what this looks like. So if we go here, I have it graphed out in Wolfram Alpha. So right here, this equation that we have is a 3D plane. So you can see that in the graph we have the labels. We have the x-axis on the bottom left and the y-axis on the right side. And then the one that goes vertical is our z-axis. So if we imagine, if we look at this plane from a top-down view, we just created a region underneath it. And that region, we're going to imagine that it's projecting up as if it's cutting out of this 3D plane. And so what we want to do is find the lengths, because again we had that plane like that was projecting. So now that we have a region underneath it like that, and so we're going to find the lengths of each side of that region, and we know where our legs are at because we just found that the legs are at these points underneath our graph. So I don't know about you, but I think that's a pretty cool, nifty trick right there. Alright, so let's go ahead and I'll show you how to do that. So now we use our x and y variables and plug them into the 3-variable equation to find the maximum and minimum value. So at this point, all you have to do is plug in the x and y value. So let's say for 0, 0, we plug that into here. So z is equal to 4 times by 0 plus 5 times by 0. Z is equal to 0. And you can actually see that in this graph, because if you imagine right in the middle of this plane, that is the point 0, 0, 0. So x, y, and z are 0. So it's actually in the middle of this plane is the point 0, 0, 0. So our height at 0, 0 is still 0. So let's go ahead and put that in there. Now let's try 0 and 18. So z is equal to 4 times 0 plus 5 times 18. Well, that's 0. And then 5 times 18, that should be 90. Alright, now let's try 20 and 0. Let's go ahead and plug that in there. So we have z is equal to 4 times 20 plus 5 times 0. That's 0. So z is going to be equal to 80. And then for our last point, 8 and 12, z is equal to 4 times by 8 plus 5 times by 12. Well, that's going to equal 32 plus 60, which is equal to 92. And so there you go. So whenever our region, at this point right here, the leg that is above it, so if you imagine that our cutout again, that is where the highest point occurs in our objective function. So right here, this is our max value, and this is where our minimum value occurs. Minimum and x z value. And there you go, you have it. So it's going to ask you what your max and min is, and so your max point occurs at 8, 12, 92, and your minimum point at 0, 0, 0. Alright, so now let's get into the story problems. Now, what I like to do in my story problems is read the problem, go back through, and highlight the important things that we need. So what we're looking for, again, we're looking for 3 different variables pretty much, because we need an objective equation that has 3 variables. So let's read the story problem. A snack bar sells hamburgers and hot dogs during football games. To stay in business, it must sell at least 10 hamburgers, but cannot cook more than 40. It must also sell at least 30 hot dogs, but cannot cook more than 70. The snack bar cannot cook more than 90 items total. The profit on a hamburger is 33 cents, and the profit on a hot dog is 21 cents. I should say how. How many of each item should it sell to make a maximum profit? Okay, so I noticed a couple variables in there. Just in the first sentence it says a snack bar sells hamburgers and hot dogs. And then it continues to list how many hot dogs it needs, how many hamburgers it needs, and how much they cost. So I'm going to go ahead and highlight my hamburgers in orange. So there's hamburgers. I'm going to say that's my X value. And then hamburgers, they must sell at least 10 hamburgers. And no more than 40. Cannot cook any more than 40. So that's an equation right there if you think about it. So if we think about X being our hamburgers sold have to be between 10 and 40. So that's an inequality. So 10 is less than or equal to X. So this is saying X has to be greater than or equal to 10. And then has to be less than or equal to 40. Because it cannot sell more than 40. Now let's go ahead and find our y variable. So right there, our hot dogs, I'm going to label that as the y variable. So it says to stay in business, again, it must also sell at least 30 hot dogs, but cannot cook more than 70. So there's another equation right there. So our y has to be greater than 30, but less than or equal to 70. Okay, so let's keep looking for some more information because we don't quite have all the equations that we need. So it says a snack bar cannot cook more than 90 items in total. Okay, cannot cook more than 90 items in total. So they're selling hamburgers and hot dogs. So they cannot sell more than 90 of each item. So our sum, X plus Y, the sum of our hamburgers and hot dogs, cannot exceed... Sorry about that, guys. So our items need to stay below 90. Alright, and there's one more thing in here. A profit of a hamburger is 33 cents and a profit of a hot dog is 21 cents. So right there, the profit, that is a third variable. The profit right there, that's a third variable. That is our Z variable. So let's go ahead, we can make an equation from our profit. So we say Z is equal to, well, it says a hamburger is 33 cents. So Z being our profit is equal to 0.33x, because for every hamburger it costs 33 cents. Or the profit of a hamburger is 33 cents, and the profit of a hot dog is 21 cents. So plus 0.21y. So there you go. Now that is just the setup. The setup is probably the hardest part about the story problems. I've said that before. But now look at what we have. We have all the information we need. We have our constraints. And we have our objective. Our objective function. Now all that we need to do is graph, find the vertices, and plug them into our objective function. So let's go ahead and do that. So first of all, let's go ahead and graph our orange function. So it says that X is between 10 and 40. So right here we know our line.
Can I please get a custodian to the main office?
There we go. So there's our X value. It is between 10 and 40. So let's go ahead, shade in that region right there. Okay. Let's go to our blue equation now. This is our Y variable. So this is saying that Y is between 30 and 70. So 30 being right there. And 70. Let's go to our green equation. So this one is actually a line where if we solve for it over here, we get y is equal to negative x plus 90, less than or equal to. So we know that it intersects at 90, our y-axis, and just has a regular negative slope right there. And we're also just notice that all of our inequalities are equal to, so all the lines are solid and not dashed. And this is less than, so we shade below our line. Alright, there you go. Now we know where our constraints have limited where our graph is, where our region is. So we know right here we have one point. Here we have another point of intersection, another vertice right here, and another vertice right there. So this region right here, that is what we're looking for. We're looking to see where the enclosure of this region right here. So we need to find out that one right there, this one right here, that one right there, and this one right here. Well, these lines, some of these lines can be pretty easy to find because they were just straight lines. So for instance, we know that this line right here, this orange one, this first one on the left, well, that's when x equals 10. And so this is where x equals 10, and then this first point is when y is equal to 30. So 10 and 30. And then the one above it is also at 10, but this time y is 70. And then this one on the far right is when, we'll have to solve for that one. Also, I think I'm missing a point of intersection. I actually have that one wrong. Sorry guys, give me a second. I showed you the wrong area. Right here and right here, that's our enclosed area right there. There we go. Okay, so again, well, this right here, this is still 10 and 30. This one right here, that one's still 10 and 70. This one right here is when x is 40 and y is 30. This right here is when x is 40, and when we don't know where the y value is just yet. And then this one right here is also one that we need to find. Okay, so let's go ahead and solve for those points right there. But we do know that at this point the x is 40, and at this point right here we know that x is 20. Well, we know that y, we can see the intersection is at 20 and 70. And then we just need to solve for that one right there. So whenever x is 40, but we want to see where the orange and the green line intersect. So if we plug 40 into our green equation, we should get that. So if we do 40 plus y is equal to 90, if we minus 40 and minus 40, we have y is equal to 50. Just like that. Okay, so let's go ahead and we'll go ahead and add our table values in here. So we said there's a point at 10, 30, at 40, 30, at 40, 50, at 10, 70, and at 20, 70. Now I'm going to go ahead and wrap this up, but all we would need to do is plug these values right into this equation. just like that. And then whenever you do that, you will get the following answers. You would get 9.6, 19.5, 23.7, 18, 21.3. So, and let's go back to our question. It says, how many of each item should it sell to make the maximum profit? Excuse me. So this is the maximum profit. So they would have to sell 40 hamburgers and 50 hot dogs to make a maximum profit. Okay, so sorry I had to wrap it up there, but I felt like the video was getting pretty long. And again, the hardest part is actually the setup. And doing the calculations, well, you should all be pretty good at that at this point. So come to class prepared with questions. I'm sure there's going to be a lot of questions because this is a pretty new idea. So come to class prepared, and I'll see you then.